Hey folks, welcome back to another Geometry Nodes tutorial. In this one, we're going to be having a look at how to create this collection on curve node group. Now this has a few options in it. It looks like quite a big node group, although Blender 4.0, so we can now collapse panels. This node group is, for a start, it's very useful as a node group, but also it's going to show you a lot about building tools, because the way that we build tools is slightly different from the way that we just build general workflow stuff or specific tooling. For example, if I was to just make a shingle generator, I might not need all of these things because I might want some of them turned on all the time, or I might have a very prescriptive workflow. But when we're working professionally, especially if we're building tools for other artists, it's important to think about the way that you build tools from a little bit of a sort of abstracted space where you can think down about the workflow rather than the specific use case. That all sounds pretty abstract, but essentially what we have here is a node group which contains obviously some nodes, but it also contains other node groups that we've previously made. Now, this is something that I come across in comments quite a lot on this channel, is people saying, oh, this is great, this is really interesting. However, what's the use case? Like, why would I want to know? And the issue is, if I'm trying to teach something, and obviously these lectures, lessons, whatever you want to call them, they're very technical. I can't really teach them any faster than we already do, which means 40 minutes is probably a pretty good place for learning how to do something, but also maintaining your interest in it. The issue with that, obviously, is if we're building tools from scratch in geometry nodes, that means we're building very low-level tools. So, for example, in the last lecture, we built a curve deform node group, and that is essentially repeating the modifier behavior for the curve modifier, right? With a little bit of extra quality of life stuff because it's geometry nodes, but essentially we're building a very low-level tool there. You can use it for everything. If you wanted the use case, bending stuff, right? So it's way too general for a lot of people to really apply. This session, we're going to be doing something a little bit different. So we're going to be taking the output from 3 previous lectures on collection packing, custom boundary boxes, and the curve deform, and we're going to be joining those together into a higher level tool with a specific use case. Now, as I said, this specific use case is not the only thing this can do. It's a very useful generic tool, right? I can create something like this bridge as well with the same thing, and as you can see, if I move this around, it's creating new arches, it's arraying them, it's deforming them to the spline, it's doing a good job. And if we look at our house example here, we have all of the same kind of quality of life stuff. So if I just select this lower annex and I rotate it, you can see that we're actually rotating the tilt on these shingles. We can come into the curve itself and we can literally just rotate the tilt, change the tilt on there, and that's going to affect these shingles. We can also move the curves around, whatever you need to do. Basically, we're packing items within a spline, but we still have the option on here. For example, I could turn off deform to curve if you just wanted the array. We can turn off snap to surface if we don't want it to actually follow the underlying surface on here. It will still follow the rotation if you have a surface, but I can just disconnect it entirely. And now it is no longer connected to that rotation. Now it's only going to listen to the tilt of the splines. So a lot of utility, a lot of different use cases that this comes in very handy for. But essentially what I want you to be thinking as we work through this tutorial is, how can I apply this to building my own tools? So obviously work through it with me and you'll end up with a really cool tool at the end of it. However, the broader lesson here is in tool building at large. Let's hop over to our start file. If you want to work along with me and you haven't necessarily gone through the previous tutorials which create these node groups, then you can find this file, which is the start file. It'll be called start, down below. If there's just a Patreon link. You don't have to be signed up to Patreon, by the way. You can just click on that link down at the bottom for free. You can just click download on the files there. So there's going to be a start and an end for this session. The start looks like this. Now what we have here is a collection info plus node. This is just a collection info node that we have some additional logic in to store bounding box data on those instances. We can now use this information, the min max data, for instance packing, which is going to allow us to tightly pack a collection of objects along either linearly, just like in an axis, or you can do it along a spline, which is more what we're going to be doing today. Both of these nodes were created in the packing collection objects tutorial, linked down below if you want to go and follow that one before you do this. And similarly, we have the bounding box grouped node here. And again, this is just a basically bounding box node, but rather than taking a collection of objects, it is just going to take geometry and it is going to separate and calculate bounding boxes based on group ID, which is essentially an integer identifier, which is just found on the mesh. So if you've used nodes like the accumulate field, this has the same concept of a group ID, which is, yeah, just an identifier, basically a way to separate the mesh. This one was created in the custom bounding boxes video, again, linked down below. Curve deform grouped, this was made in the previous tutorial that was on this channel, and again, linked down below. This is just the curve deform modifier, essentially, with a little bit of extra data, extra quality of life stuff that we can play with. And we're actually going to be extending this one a little bit in this session, just to create a little bit more of a specific use case here. All right, I have all of these marked as assets, so I'm actually just going to delete these right-hand two because I do not need these at the beginning. They will continue to appear in my list. Well, they would continue to appear in my list regardless, but if I restart Blender, then they will not be purged as orphans already. In my start file, I have a collection of objects with just a icosphere, a Suzanne, a cube, just so that we have a little bit of a point of reference here. And I'll go back to my geometry nodes object. I'm also just going to add a Bezier curve. If I go full screen here, I'm going to scale this one up, and I'm actually just going to duplicate it a few times here, just so that we have multiple. Maybe I'll do them in a non-continuous order as well, just so that we get the flow over being inconsistent, which I feel like this is one of those things when you're building tools for yourself, you know the limitations of the tool, so you can create art within the limitations of a tool. If we intentionally create slightly unpleasant starting conditions like we have here, the good thing about this is that it's going to force us to start doing a little bit of bug testing kind of as we work to make sure that we can deal with, you know, things being in a different order or things being different sizes or rotations or whatever. It just helps you to build more robust tools. So I'm going to create a new collection for my curves. I'm going to drop all of these Bezier curves into here. And let's go back to my geometry nodes object here, which is just a plane with a geometry nodes modifier added to it. And I've named my geometry nodes modifier deformed array, just so you know what we're working on here. To clean up these two node groups, let's just select them both, right click, show hide node options. There we go, that's got rid of that little group picker thing. And the way that these two node groups work is our collection info plus node wants a collection of objects. Here we go. We can see that we have these in our node group now. And we're going to be using the instance packer to basically find out some data about them. Now, the instance packer doesn't actually pack instances, it just tells us where to pack them. So what we want to do, join these up, min and max. There we go, nice and joined up there. If you want to know more about how this works, I do recommend that you check the tutorial on how we built it, because that will give you a real lowdown on how that works. But just to kind of give you a very simple overview now, if I take a bunch of points, just with a points node there, I'm going to set the position, and let's just view the output of this. Let's make, for a slightly larger radius, let's go into solid view. Let's make 50 points, and we're going to offset the position by the, let's go in the x-axis. That's what we're going to be working with in this whole tutorial, just the x-axis. So we have this length vector. Technically, that's going off, 45 degrees, because it's combining the x, y, and z offset based on the bounding boxes. If I just multiply this with a vector math node by 1 in the x and 0 in y and z, that's just going to give us that x offset. And then we can take an instance on points node on here, and we'll take our instances from the collection info node, collection info plus, which we will set to pick instances. And now if I have a look from the front, you can see that all of these are neatly packed in. Let's go ahead and add a little bit of extra detail in here. So rather than this just being a repeating series in order, we can control the instance index on our instance packer. And this will pass out an instance index, which will go to our instance on points node. So let's build this up. Let's take our instance index socket. We will plug that through a random value. 0 to 100, that works for me. You can now see that all of our offsetting has gone wrong. And the reason for this is because we are not instancing the same object that we are calculating the offset based on. Hopefully that makes sense. Let me show you if I plug in, well, I can either do it this way, so random value up into here. Now you can see, okay, these runs are a little bit wider. They're all now packing correctly, but it's a little bit easier, a little bit cleaner if we just daisy chain these through. So it's just passing through that instance index. Bring these down here. Instance index into our instance on points, and we get the correct packing. What about scale? Well, let's do the same thing. We're going to take our scale. We're going to take a random value node. This one, rather than it being vectors, we are going to go with a float, just so it's a sort of continuous size. And again, we're going to take our scale output into our instance on points node. And there we go. Now we can see we have the correct packing, things are working nicely, and the scale is working. So we have everything nice and tight up against each other within this simple linear array. So that's how this node works. We just need to push this a little bit further to be able to get it to work along our splines, because we have all of these curves in here that we've just created. Let's make it relevant. Because we're working on multiple objects, I'm going to pin my node group just so that I have this permanently. Let's begin with a little bit of cleanup. Just before we go any further, this is something which is going to be really useful to you when you start building tools, is learning how to effectively group things. So let's go to that viewer. I'm going to join all of these together, Control G to put them into a group, and tab back out. We're going to name our node group to begin with. So this one is going to be collection on curves. Let's go back in. And we want a few bits of information. So we want to connect up our collection of objects. This is going to be one of the main elements. However, this is really important. Do not just connect a socket into like an object picker or a collection picker or a material picker that is already populated. The reason for that is that if you append a node group that has a sort of a hidden default data block, then it will bring that data block with it. So even if you're looking at it from the outside and you're saying, oh, this is empty, when you append it, because there's a default, or Blender thinks there's a default, you're going to end up with just importing loads of rubbish data, and you don't want to do that to your artists, right? If you're working on a team with other artists, you don't want to be contaminating their scenes. So the first thing we're going to do here, let's get rid of that input. We're going to simply remove anything from our data block here, and then we're going to join up. So that's our collection. Another thing that we want in here is going to be the seed for our random value. So let's take our new socket down to that seed. And I'm also going to plug this seed with a new group input into our random value down below, the float, which is controlling our scale. And then we're going to make our scale a little bit more intelligent. So rather than just having a random value controlling the scale, we want two bits of information. We want to be able to define the scale, and then we want to be able to randomize that scale. So just working on this lower section down here, we want to know how Blender treats scale. So we're going to bring an instance on points down, because we want to make sure that all of our UI, all of the experience the user has with our node group is consistent with Blender. That is the software they're using. We want to make sure that their experience is consistent. So let's just bring in the scale over here. And I'm actually going to add a new panel into our interface. So on our end panel here, we are going to add a new panel. And this one is going to be called transforms. And I can simply drag and drop this scale within transforms. We are also going to be doing rotation, and this needs to be in transforms as well. I'm going to disconnect that just because we're not actually dealing with rotation right now, but just for the sake of having it with the correct UI. So if I come back here, you can see that our scale is saying XYZ 1111, and rotation is saying XYZ 000 degrees. Okay, so that's all nice. And this panel is collapsible. So that's one of the reasons that we're using 4.0 here, one of the new features. Also the order, by the way, rotation and then scale. That's how the instance on points node does it. So that's how we do it. I don't actually need this instance on points node. I was just stealing the sockets. So we can delete that now. And what we want is to now modify this scale. So first things first, we're just going to use our scale directly, right? So this is just the scale that we have defined on our group input. That is going to go to the instance packer node. Now we want to modify this by some amount based on the random value. So what I like to do, I'm going to take a vector math node, which is in utilities vector math, and I'm going to use a function called multiply add. Now what multiply add does is it will take an input vector, it's going to multiply it by something, and then it is going to add another vector. The reason that this is an operation, a specific operation, is because CPUs, the hardware, is very fast at doing it. In fact, it takes the same amount of effort for a computer to do multiply add as it takes for it to do a multiply or an add, right? These are like a single cycle operation, so very fast for you to work out. What I'm actually going to do is I'm going to take my random value, which I'm going to put between -1 and +1. I'm going to pretend this is my vector. We're then going to multiply this by a 0 to 1 scale. And so we're going to add a new input. It's a float of subtype factor between 0 and 1. And this one is going to be called randomize scale, just like this. So if we have a look at the outside of our node group, now we have a slide between 0 and 1. So a nice little factor slider. And this is controlling how much randomization our scale is getting. So we have our random value between -1 and +1. We're going to be multiplying it by some factor between 0 and 1. And then we're going to be just adding this to the defined scale. So let's say our scale was just 1 as defined. Then we're going to be adding that 1 to values between -1 and +1. So now we will be basically scaling this between 0 and 2, and that randomization is just going to give us a little bit of leeway, a little bit of wiggle, and you can change this as well if you wanted to. The good thing about these values is these are only soft limits, so if I wanted to go to 5, I can do. So there we go. This is now our scale. We're going to just frame this up. Another thing about making tools for other people is you want to make sure that they are readable. So Control J, select that frame, F2. This one is for randomize scale. Now, we also have on our instance packer, if we just join, we collapse that side, we're going to connect our instance on points node just to the group output there. And we're going to connect this now to our main group output. There we go. So we can view it, and we're going to define our collection as objects. There we go. You can see now that as we increase that randomized scale, we're getting that randomness added into that scale. So on our instance packer, we have another option for spacing. And what this does is it simply adds a fixed value in between each of our instances. I'm going to set this back to 0, and I'm just going to connect this to our group input there. Now, if you're wondering, if you're new to 4.0, the reason that this just jumped back up to the top section is because it is going above this transforms panel. So when you add a new input, by default, it's at sort of a base level. And so it's coming above the panels. Any panels that you have, you can't just put base level inputs below a panel. So there we go. Now we've added spacing. For the next few minutes, we're going to be building this up onto our splines. So let's work out how to do that. Back in our end panel, we need to create a new input up at the top here, which is going to be a geometry input, and we're going to call it curves. Now if we tab back out here, let's bring in our collection of curves, these ones here. So I could do this as an object, or I could do it with a collection. And again, this is one of those things where we're doing it in kind of the inconvenient way. Obviously a collection is convenient in terms of it actually holding everything together. But in terms of workflow, what this is actually giving us, rather than just bringing in a single curve, is a collection info node gives us instances, an object info node gives us geometry. There's certain things that you cannot do to instances. Things like geometry proximity, sampling from one to another, makes it more difficult to use instances. So by forcing ourselves to plug in instances, we're ensuring that the tool that we create is more robust, more usable, because we don't want people to have to think, oh, I now have to also add a realize instances node manually. We're going to do that for them on the inside whenever we need to bring in that data. Take our group input node, we're going to bring it up to the top here, and we're going to import our curves. We are going to first of all realize the instances, because that's going to give us the actual geometry data. And then what we want is to sample the positions that we want to position our instances. So let's go ahead and do that. Let's take our realize instances through a sample curve node. And we have a bit of information. So how are we going to use this? We have points that we've created, and rather than using the length as the offset, because that's just going to give us an array in the x-axis, what we want is to set the position based on the sample curve. So now we're going to define an explicit position. Now if we have a look at this, it's not quite done what we want. If we have a look at the sample curve and I move along the factor, well, everything just moves along this first curve. I could change the curve index to get it to move up onto a different curve, but that's not really what we're after. Let's change sample curve to be all curves. So now you can see that we sort of overflow from one to the next, to the next, to the next. And instead of factor, which is just 0 to 1, we're going to change this to length. So now it's a defined length along the curve. We have length on our instance packer, so let's use this. Let's separate XYZ, that length. I'm actually just going to move my curve group input and realize instances up above. We'll come back to those a bit later. For now, we're just using them as they are. So we're going to take our length, the X component, and there we go. So now we can see that these are moving along here a little bit better. Let's actually just reduce our scale just to make this a little bit more appropriate for where we're working. Somewhere around there is probably fine. Let's go to 0.4. And we'll come back in. I'm going to collapse that node. That was Control H for hide. So now we're just basically finding the position along the curve at every length that our points want to be. We have another issue that we need to remedy, and that is that our final one here has a lot of overlapping geometry, and that's because we've created 50 points, but we don't actually have space for 50 points. So we need to do two things. First of all, we need to make sure that we have enough points, because, for example, if I set this to 10, then we would have too few. So we need to make sure that we have at least as many points as we're going to need. And then we need to delete any points which are too long, essentially, that the length is longer than the length of curve that we have available. So first part of this, making sure that we have enough points. Now you could do this analytically by just looking at your randomized scale on here and calculating what the potential minimum would be. Rather than doing that, I'm actually just going to use attribute statistics because I'm lazy, and it's all right to do things which are lazy if they are still fairly quick and they're readable. I think readability is really important when we're looking inside a node group because it's going to allow people to tweak it and make adjustments based on their specific use case. So what we're going to do is we're going to take another points node. We're going to create 100 points. That's probably quite a good subset of points to estimate. And what we will do is use an attribute statistic, and we're looking for a float value for what the minimum instance size is going to be. So let's take another separate XYZ. We're going to take our instance size. So we can use the attribute statistics on this attribute to find out what the minimum value is here. So for these 100 points, we have in our point cloud a minimum value here of 0.415. So that is the smallest size that any instance within that 100 sample is. Now obviously this is only 100 sample. If I went to 1,000, for example, then you can see that we go even smaller. However, I'm not too worried about doing that because so the more points that we use here, the longer this statistic is going to have to take to calculate. But also, when we're using a random value, the randomness is very unlikely. The probability that you have a seed where everything is at the smallest size is negligible, right? It's just not going to happen. So what we can assume is that because every time we have something small, we just need to approximate what the smallest one is going to be. And then we can use that to create as many points as we need and be confident that we will end up with more points than we actually need, because in reality, randomness goes both ways. We're going to be going up and down. So how do we use this? Well, we have our curves up here. We're going to be using a node in curve read. We're looking for curve length. So there's two nodes in here, spline length, curve length. What's the difference? Spline length is a field, and curve length is just a static value, a single value based on the total curve length. So basically the sum of all splines is the curve length. And this is what we're after. We want to know what is the gross length of all splines present. Let's take this. If we divide that length by our minimum size, so if we had 100 in our length and we divided it by a minimum size of 2, then we would have 50 points. In this case, we have 41.949. We have a minimum of 0.415. And so we're going to be generating 101.14 points. I can just plug this into my points here. Float going into an integer, this is going to floor. So rather than 101.14, we're going to get just 101 points created. Okay, let's clean this up a little bit. Control H on that attribute statistic to collapse it. I'm going to just collapse that points node as well. Frame these up. Control J to frame, F2 to rename. This one is estimate min size. So now we have enough points. Okay, and we're pretty much guaranteed that we're never realistically going to not have enough points. Now we have the other problem. What do we do about this overflow? Well, let's move our instance on points away. And we're also going to do this before the set position, because set position is doing some calculations. We want to do it while it's as light as possible. Let's geometry, operations, delete geometry. We're going to be deleting any point where its length, sorry, from this separate XYZ here, any point where its length is greater than the curve length. So just like this. So when the length of the point is greater than the curve length, we know that we have gone too far. And you can see that there. So if I mute and unmute, every point, every instance which wants to be beyond the final point is removed. All right, we're getting there. We're getting there. So we've just deleted a whole load of points. How many was that? We went from 101 to 44. So we just deleted more than 50% of our calculation for the set position. So we're optimizing here as we go as well. Not going to use selection or offset, so let's go Control H just to collapse that node down as well. The next thing for us to see to here is going to be rotation. So we can have a look at all of our points, but these are all just kind of going all over the place here. They're, yeah, nothing is following the curve, and we want it to. We want it to follow the curve. So let's use our sample curve, tangent, and normal to control the rotation of our instance on points node. So let's bring this down. We'll clean up all our noodles once we've got a little bit further here, just to make sure that we're filling things in nicely. So the first thing that we're going to do is going to be taking our tangent through an align Euler to vector as the vector, not the rotation. It's got to be the vector. We're going to be aligning the x-axis, so the horizontal axis of our instances, to the tangent of the curve. And this is the x-axis because we're doing our packing sort of horizontally. If you were wanting to do this with the z-axis, then you would need to make sure that you were using the z-axis of your instance packer to work with. So x-axis, pivot auto, that's all fine, factor at 0. Let's just join this into our rotation. There we go, that's a lot better already. The next thing that we want to do here is, well, let's talk about it. So tilt is something that we have, an attribute that we have on curves that allows us to basically rotate them around the tangent. I can set this up very simply with another align Euler to vector, just daisy chained. If I take the normal into my vector and I plug my y or z or something into that normal, then you can see as I press Control T, I get some tilt going on and I can spin these around. Now, the problem is we're building a tool here where we want as much flexibility as possible. So we want to use tilt, but we also kind of more importantly, want to be able to understand a surface. So for example, if we're building shingles, if we're building a terrain with a bridge or a path system, whatever it is, we more often than directly using tilt, we want to align to the normal of a surface. So rather than the normal of the curve, we want to bring in a surface at this point. We do also want tilt, but we want that kind of secondarily. Hopefully that's not too abstract. As we build this up, it'll become more obvious what's going on. So rather than using the normal from the sample curve node, we need to now create a surface. So again, just to make sure this is bulletproof, we're going to add a new collection called surfaces. And I'm just going to add a plane in here, which I'll scale up a little bit. Just something like that is fine. And I'll put it at an angle just so that we know that we're expecting a change here. Again, let's tab back out. We're going to bring in our collection of surfaces. We're going to make sure that both of our collection infos here are using relative, just so that we have the local transforms on these. There we go, that's a bit cleaner. And then we need a socket to plug in our surfaces. So again, let's tab in. I'm going to create a new input. This one is going to be called surfaces. It's going to be a geometry input. And it's going to take our collection. Let's tab back in. Let's find the surface normal. So we're going to add a group input. We're going to take our surfaces. These could be, as they are right now, an instance. So we want to realize instances to begin with. Then we want to add a sample nearest surface node, which is under mesh sample nearest surface. And we're sampling the vector, which is going to be the normal. There we go. Let's just plug this into our next align ordered vector. Here we go. And we're actually going to be aligning the y-axis here, pivoting around the x. So you can see that there. When that was just set to auto, these were all a little bit twisted, but we've already defined the x-axis. So we want to align it pivoting around the previously defined axis. So there we go. Now these are all facing down. Something that you might want to do, just check it, just rotate it around, make sure it is working how you want. And something that I might do is just invert this normal. So I'm going to use utility vector math, which I will set to scale of -1. Reason being that I kind of want these to face up. I find the way that I work is often sort of facing y negative, like Suzanne does by default. So when I want her to face in the direction of the normal, it's helpful for me to just invert that normal there. Again, readability, super important. Control J, F2, this one is surface normal. Let's just call it that. So the next thing that we want to do here is just double check that this is actually working. Now, we've sampled the nearest surface, but the normal for the entire surface is the same. It's all one plane. So what I'm going to do, tab into edit mode, Control R, let's create a load of loop cuts in here. Go to my end edge, turn on proportional editing, and I'm just going to rotate it in the x-axis. Just like this, to create a little bit of a twisted geometry. And I might also just create some horizontal cuts. There we go, just a little grid with a little twist in it. And now we can see that as I move this in the x-axis, it definitely is using the correct faces. It's always useful when we're debugging, when we're just making sure that things work, that you do little ways of testing that something that you're assuming is working is actually working. Because nothing is more annoying than giving out your tools to people and then having them come back and say, oh, your indexing was off by 1 or something like that. Let's come back in here. We're going to be now sampling tilt. So that's the next thing that we want to do. Right now, if I take this and I rotate it, nothing happens. So if I set my mean tilt, this is under the item tab of the N panel, the information panel. In the 3D viewport, you can set your tilt in edit mode. I'm going to just set this to 90. So when we have this working, we will expect Suzanne to be looking forwards or backwards, either or. She should just not line up with everyone else. So the way that we're going to bring in tilt is fairly straightforward, actually. I want to make a little bit of space to the left, just so that I'm routing these noodles around here. I'm bringing my curve stuff down. So we're going to be processing our curves a little bit later. So this is why I'm not just kind of duplicating these everywhere I want them. We're going to be processing them a little bit later on. This is something that I can only really tell you with foresight. If we were making this organically, I could say, then you are absolutely fine to make mistakes, obviously, as you're working through. And they're not necessarily mistakes. It's just things that need re-engineering later. So don't be afraid to just try stuff and hope it works. But right now, we're just going to take our curves as they exist in our node graph. We're going to bring them down and then we are going to sample them. So first of all, let's resample these curves. Why am I resampling the curves? Because we're using Bezier curves. We're going to resample evaluated. Thing is with a Bezier curve, and I'm sorry if you already know this, but just for the sake of clarity, Bezier curves have handles. By default, a Bezier segment like this will have two control points, each with their own handles. All of the rest of the curve is technically not being evaluated. So if you instance directly on a Bezier, you'll notice that you get your instances only at the ends rather than all the way through. So what we're going to do is we're going to resample this curve to make all of the actual curve positions into points that we can use. Now, why evaluate it rather than count or length? Well, if we could set it to length and just do something really small, but this doesn't necessarily factor in everybody's workflow. Maybe you're using this for something architectural, in which case using 1 centimeter like this would be completely inappropriate because you don't need that much calculation. So what we're going to do is we're going to use evaluated. That is going to use whatever points the curve has visibly in how it's been set up. And that means that the user can come in, if I just isolate this, if they're setting up their curves when they're creating them and they're using these render previews, this is the evaluated point, right? And this now means, oh, well, we're leaving this up to the artist to say, okay, well, this one is only going to have 3 points or 4 points because we want them to have the control over the art that they create. So rather than making decisions for them, we can rely on their decision making to be appropriate for what they're working on. Let's come back out of local mode there. So evaluated. So then what we're going to do is for each of these points, if we find them here, let's make them a little bit smaller. So these points, each one, we're going to find the tilt from the nearest curve position. So let's find a sample nearest. Here we go, sampling the nearest point. This only outputs an index, so we also need a sample index node. Let's plug this through. And the value that we are going to be sampling, this attribute, is going to be the tilt, curve tilt. There we go. Now you might have noticed a problem with this, but we will come back to it in just a moment. Let's try and plumb this through. Because we now have an Euler, we're going to use the rotate Euler node. So it's under utilities, rotation, rotate Euler. You'll notice in 4.0 there's a lot of new rotation nodes. We don't actually need them in this tutorial, but just to be aware that they're there. So we're going to be rotating. We're going to be using axis angle for this. And this is because all of our points, all of our objects, these have been aligned around their x-axis. So we want to rotate the tilt around the local x-axis. And we're going to use that tilt that we just found into here. Nothing is happening, even though we were expecting this one to rotate. So that's why we sort of preset up that tilt. If we have a look at our nodes, we can see an exclamation mark. This says unsupported geometry type curves. So the sample nearest actually needs a mesh. So just on this bottom noodle, we're going to use a curve to mesh node like this. And there we go. Now we can see that that rotated those instances towards the tilt. Organization is key. Let's go ahead, select these nodes, Control J. This one is going to be sample tilt. And there we have it. That is our tilt being added. So now we can come into our curves. Let's full screen this. Go into our curves, and I can use tilt to then sort of add a compound rotation on top of this surface normal alignment that we have. Do we want to do anything else for the rotation? Yes, we do. We want to add a random rotation on here, and we're going to use the same idea that we used for the random scale. So quite simply just duplicate this frame down to the bottom of this little rotation stack. This one is going to be renamed F2 to randomize rotation. And rather than, let's just dissolve these reroutes. Let's take our random value. We're going to change this to a vector. And also, what we want to do is, instead of using the same seed exactly as everything else that we have before, we're going to be using a math node to just add 1 to that seed. The reason for this is that something which has a small scale, we do not want to have a small rotation. We want to make sure that the scale and the rotation randomness are separately randomized. So we're just going to alter the seed like this, add 1 to that value. Now, before, for the scale, we went from -1 to +1. Similarly, for the rotation, we're going to be going from -pi to +pi. Remember, when we're working with computation, we're generally going to be using radians. So -pi to +pi is -180 degrees to +180 degrees. Similarly to before, we're going to just plug this into our multiply add. Let's bring up our N panel, just make a bit of space. We're going to come in under our rotation. Let's add a new input socket, which is going to be called randomize rotation. It's going to be a float of subtype factor between 0 and 1. So basically a scale between 0 and 1. The reason we're using 0 to 1 is because when we multiply by 0, we end up with 0. So no randomness. And when we have 1, then we have the whole amount that we're defining in here. Let's just unhide those sockets. We're going to swap this up. So we're going to use randomize rotation as our multiplier. And then we're going to use the rotation as defined on the front of the socket as our add. So we're simply adding some amount of the random rotation to a predefined rotation amount. So just the same as the randomized scale, we're just using it for rotation here. And again, this is something which I quite like to do in tools, is having a consistent way of processing. So if somebody has broken into this and they've taken the time to learn what you're doing, they can see, oh, the way that they're doing this is the same over here, is the same over there, is the same over there. I understand that and I can work with that, rather than needing to learn something every single time they try to come to a new part of the node tree. So randomize rotation, we're going to come in, we're adding another rotate Euler node. This time it's an Euler rotation, again in the local axes, and we're just going to plug that random value up into our rotate by socket. Okay, things are starting to look pretty good here. So we have some random rotation that we can add if we want to. We can maybe rotate these in the x-axis, and you can see it's their local x-axis. So we're sort of adding a global tilt essentially, but we can also rotate in the other axes as well if we wanted to. And with this panel, we can just collapse those transforms if you don't want to use them. So this is going well so far. We need a few more things though. And something I like to do, I always put seed at the bottom. So let's put spacing just above it in there. That's just click and drag to move these around. The next part of this tool is going to be, rather than packing our instances, perhaps you actually just want a fixed offset. So instead of, using our instance packer information and all of this, this smartness that's going on inside this node group, perhaps you actually just want to say, every object is going to be offset by 1 meter. Or 500 centimeters, or whatever it is. You want to be really explicit about what that positional offset is going to be. So we're going to do this in a really kind of cheap and easy way. We're going to take our curves, and I'm just working before all of this stuff where we're creating positions, creating points. And actually, let's just frame that up. Let's frame a few things up. Just before we move on here, let's make sure that we're staying organized. Select all these rotation nodes. I'm just going to move these ones down. I'm going to take this section of the align Eulers and rotate Euler. We're going to rename this to rotation. And these ones where we're generating the points for the packing, let's select all of these, including the sample curve. Control J, move these up a little bit. Let's rename this one to points for packing. So we understand what's going on with these parts. So just before this and in parallel, I'm going to be taking my input curves which have been realized, and we're going to be simply resampling them. So resample curve with a specific length in between points. That point distance is going to be the sort of the spacing between our like arrayed points along our curve. This is kind of a cheap and easy way. If you have a curve, something like this, and we say that we want to resample the length, it's not going to do an exact length in between segments. It's going to find the closest thing it can that fits exactly within the length of the curve. For this, I think that's fine. If you do need to be a little bit more prescriptive, then you can modify the other stuff that we made. But I think for this, it's going to be absolutely fine. I've never had an issue with it. Let's take our group input and we're going to create an input for the length. Or are we? So we have all of these things already available on the front of the node group, and we want to make sure that we're not overwhelming our artists with just sliders and things. Now, doing a fixed offset is going to be an option, right? So first of all, before we go any further, let's come up onto our end panel, make a bit of space. Just at the top here, underneath our collection, we're going to create a new input. This one is going to be called fixed spacing, and it's going to be of type Boolean. There we go. Default is going to be off, and I would recommend as well, if you're shipping node groups, you do a little description so that when you have hover help, you know, when you like hover over something, it's going to tell you a little tooltip in here. So if I do a tooltip, then when I hover over this, you can see that we have tooltip at the top there. So this is an option that is going to be able to be turned on or off. Now, when it is turned off, if I were to add another option in here, another slider for the distance in between those fixed spacing points, what you have is a dead slider, and dead sliders are the death of user experience. They are awful and they will turn people off from what you're working on. You do not want dead sliders. Do your level best to avoid them at all costs. So what you want instead is to try and find a way of wording what you have that can be applicable to multiple options. So for example, in this case, we have spacing that spaces out our objects. However, when we turn on fixed spacing, perhaps the spacing becomes the fixed spacing distance. So let's come in here and try this. We're going to go and connect our spacing input to that length. And then because we want to be able to swap between our points for packing and these resampled curves, what we're going to do is simply use a switch. So utility switch with the resample curve going into the true socket and the group input here. Let's take our fixed spacing as the switch. Now, don't plug this in just now. First of all, what we're going to do is save, because this can potentially crash. So go ahead and click on that switch. You'll see that we end up with just points at the beginning. So it hasn't really worked exactly as expected. Let's go in here and let's change our spacing to something very low. So I've gone for 1/1000th of a millimeter in between each point. I can hear my CPU starting to spin up, and there we go. We have a lot of instances. So when our spacing is extremely low, as it will be in general, because for the most part, you're probably going to be using a spacing of 0, or you might have a very small positive or negative value in there. For example, just a little bit of an overlap. If I have a very small value like this, you can see that we've just created over 3 million instances. That is not exactly ideal. These are very simple geometries, and Blender is still behaving extremely slowly. So we want to make sure that there is a lower limit on this. And now this does mean that I'm making a slight decision for artists. I'm basically saying you cannot work with a fixed length, which is less than, in this case, we're going to say 1 centimeter. However, it's also a safeguard, because it means that, you know, if they need to, they can come in, find this value that we're going to be putting in here, and they can change it if they need to. But it just prevents them from crashing their computer unnecessarily. So let's come in. We have our resample curve. We have our spacing, and rather than using this directly, we want to use a math node, which is going to be set to maximum. So what this node will do is it will output the maximum value between the spacing and whatever value we have in here. So this is going to be 0.01. And then we can just plug this up into our length just like that. And there you go. Now you can see that we have something which is a little bit more limiting for sure, but it does mean that we're not going to be crashing people's computers and then you're going to have unhappy artists. So we don't want to have that. So let's go and make sure that we have our Boolean plugged into that switch. There we go. So you can see that we can now change this between those two options. So we can set our spacing back to 0. And it's actually limited now to a spacing of 1 centimeter. And we can turn off fixed spacing if we want to go back to our properly packed version. There we go. Now, when we're in fixed spacing, let me just show you something. As we move this down our spacing, something's not quite right with how this is moving along here. And the problem is actually that when we are using our rotation, the first thing that we do is we use the sample curve based on the length from our instance packer. So this is actually not the tangent at the position of these points. That's a problem. We need to make sure that when we have fixed spacing turned on, we're also going to be using the tangent from their own curve rather than trying to sample the position based on some other calculation. So just before I align Euler to vector, go ahead, grab a switch node, grab a vector, and we're going to be making sure that, again, we're aligning this with how we set it up before. So we want to use the true option with the curve read curve tangent. So let's plug this into our true here. We're going to use our fixed spacing Boolean. And there we go. Because we're working on curves directly with this one, when we turn that off, you can see that we're actually just on points. So we can use the curve tangent directly when we're using this top branch here, which is just resampling the curves. So now we should, and do, I believe, have a correct approximation for the tangent. So let's tab back out. So when we have our fixed spacing on, if I reduce this, you can see that these are following the curve nicely there. So that's exactly what we want it to look like. Go back to our fixed spacing. Let's set my spacing to 0 so that we're just packing nicely. Sorry, turn off fixed spacing. Next thing that we want to do here is actually find a way to snap these to the surface. So in the case of a roof, you might want to have your shingles actually following this guide surface physically, the positions of them actually stuck to the surface. So your curves are just there drawn in by hand potentially, just to give a sense of where things can go, and then sticking them onto the surface that you need. You might also be doing this for character rigging or character accessories and things, clothing, where perhaps you want to be creating stitching, necklaces, jewelry, whatever it might be, zips, and you just want to draw this on, but you want it to stick to the surface rather than actually following your curve directly. So curve acts as a guide, surface acts as a sticky surface. This is the reason that we kept our curve processing separate at the beginning here. So let's come in, let's bring in a bit more information. So a couple of things that we need. After the spacing, we're going to add a new option, a new input. This one is going to be called snap to surface. It's going to be a Boolean, and that's it. Default is going to be 0 or off. So we have our group input, realizing those instances for the curves. I'm going to have another group input. It's quite handy to have these all separate just so that you can control where your nodes go. We're going to take our surfaces, again, realize those instances just in case it's a collection, as it is. And we're going to use the geometry proximity. Geometry proximity allows us to basically find the position that is nearest to each evaluated point on faces, edges, or points. In this case, we want faces because we're sticking it to a surface. And we just want that position. So what we can do is we can set position of our curves. And I'm doing this parallel because this is an option. It's not the way that we want to work. It is an option for a way that we might want to work. And I'm going to set this position into the position here. And we're going to add a utility switch node. Just drop this on here. Goes into the true option. another group input with our snap to surface boolean coming in. And just for now, I'm going to use Control Alt, right click and drag just to mute that, just so that I can actually control it myself. So if I just use that by default, it's actually not too bad what we've got going on here. But again, we're running into the problem where oh yeah, there we go. That's really clear. So you can see our highlighted lines here, these orange ones, hopefully anyway. Let's go for a slightly darker surface color. So there we go. So we can see that these curves, they have been snapped to the surface, technically. The positions that we can control on these curves, the control points, have been snapped to the surface. However, they're Beziers, which means that the rest of the curve has been sort of ignored. We've just positioned the control points. So when we're working on snapping to the surface, what we want to do is, again, resample, which is under curve operations resample, based on the evaluated curve. So again, this leaves the control down to the user to make it work for their use case. And now you can see that these snap correctly. Organization is key, Control J, F2. This one is snap to surface. There we go. Then we've got this switch at the end. Unmute that noodle connection. And here we go. Great. Reroutes always make everything look professional as well, so go ahead and use them as much as you can. So now we have this option for snapping to the surface. It is happening on the curves before anything else is calculated. Right, so we're not doing all of our calculations for rotation and then we're positioning the instances afterwards. No, we are moving the curves themselves, snapping them to the surface, and what that means is that the tangents are still consistent across them. Even if they get stretched or bent or whatever it is, to conform to that surface, all of your tangent data is going to be following the surface at that point. So that is what you want. There's one more thing that we want to add here. I know this has been a fairly long tutorial so far, but we do want to add just a little bit more of a usability thing here. Let's go back to our flat shading. I'm going to turn off snap to surface and I'm going to show you something. Let's say, and actually, you know, I might just hide this surface as well, just so that we don't have to look at it. So we have all of our curves. Let's say that I wanted to select them all, go into edit mode. So if I wanted to make these fit in a particular place, then you can see that this is a problem, or it's certainly challenging, because every time I move one of these, all of the positions of the following ones, except from this one, which is last, get moved. And this is actually something, this is the reason that we made these in non-consecutive order. This is why it's 0, 1, 3, 2 in order that we made them. Because it's really easy to think, oh, well, you know, I'm just going to make this first one fit, and then we're going to move the second one and make that fit, and then we're going to move the third one. That's really easy, and then I can just make this last one fit. But in reality, you might have put marks in the middle or whatever it might be. You might be trying to align your shingles, and then it's like, oh, every time I move this one, which doesn't quite fit, everything else moves. So we want to deal with this. We want to make sure that our instances are being deformed to these curves, so they're being properly stretched to the curve bounds. And that is going to make it very easy for you to then make very fine-tooth adjustments. How do we do this? Well, actually, not too difficult. But we're going to need to make sure that we have a little bit more information about what's going on. We started off with a couple more node groups. We had the bounding box grouped, and we had the curve deform grouped. Select both these nodes, right click, show hide node options. There we go, clean them up. So before we jump into actually working out how to do the nodes for this, we want to make sure that we understand the curve deform group. If you want a real deep understanding of how the curve deform grouped node works, I recommend that you have a look at the last tutorial where we actually build it. It's going to give you a much deeper understanding than what I'm about to say. But essentially, what we can say is if we have a cube and we need a little bit more resolution, so let's up this to 100, just so that we have the points to deform. And I'm going to need a Bezier or some kind of curve. And let's plug this into our curve deform grouped. We also need min-max data, so let's use a bounding box node just to get that. And then we also need a set position node. on the end, which this is going to go into. This disappears, so the Bezier segment doesn't actually have a radius attribute. So let's just set radius. Yeah, set curve radius on our Bezier segment. Let's set this to 1, just so it multiplies by 1. Increase your resolution there a little bit. There we go. All right. You can kind of see, hopefully, what's going on. We're taking our cube. We are deforming it in the x-axis, in this case, along our spline. Now it's being controlled by the radius as well, but essentially that's it. So fairly straightforward, logically thinking. I mean, there's a bit of thinking inside here, but in terms of how we're actually going to use it, what we need to think about is we have our instances, we want them arrayed in an axis, and they are going to be deformed from that axis onto the curves. So rather than having them instanced along curves and then sort of stretched to fit, we need to actually create a different array of these instances where they are aligned to an axis. So this gives us a couple of little things that we need to work on here. And now there's another thing that we want to work on is the group ID. So we have this bounding box grouped and curve deform grouped, and we're using these because it's important that each curve gets specific objects. And we need to make sure that we're mapping and tracking what those things are. So this is all sounding quite high level. Let's just jump into it and hopefully it'll make sense as we go through. So first things first, we need to create an array along the x-axis of our objects. And we'll undo a few things as well as we come along here. So I'm going to use another instance on points node. We are going to be using the exact same scale. So let's join this up. We're going to be using the exact same instance index. So let's join that one up. And rotation is going to take a little bit of thinking, so we'll come back to that one. Instances, exactly the same instances, so let's join that up. And the points, technically, we're using the same points, although we're going to reposition them to be axis aligned. In this case, the x-axis. Let's just, let's do this. We're just going to add a switch in between these two here. So let's just put this on. Top one is going to go into the true socket, so they're going to cross over. And on our group input, we're going to add another input, which is going to be called deform to curves. And this is just a Boolean, just with the default being off. Let's add our group input, which I will plug in with that deform to curves input. And I will press Control H to hide. And I will also just mute this noodle for now so that I can force it on as we're working. Okay, where do the points want to go? So this array, I can't just say, let's just stick them to the x-axis in their current positions, right? So if I were to say, just take a set position node on these points, and I'm going to take a position socket, so a position input node, multiplied by 1 in the x, 0, y, and z, and that's the position. This isn't right. This isn't what we need. So what I'm actually looking for is to array these based on their length or their position along the splines. So we still want to maintain the packing if we're packing them, or if we're doing a fixed spacing, then we still want to maintain the fixed spacing. So we need to store that data. I'm just going to capture it, keep it nice and lightweight. So let's go ahead, attribute, capture attribute. On our points for packing, I'm going to be storing the length from this separate XYZ. Not just the length though. Because we want each of these instances to end up on the correct curve, and our node groups, where are they? Up here. Our node groups have this group ID integer. We're also going to be storing an integer for which curve index we're assigning them to. So rather than just a float, we're going to be storing a vector. I'm going to use a combine XYZ in here. Now the x-axis of this vector is going to be, let's make a bit of space, here we go, is going to be the x component of the length from our instance packer. So that is going into the x. Let's use some reroots in here, just to make sure that these are where they gotta be. So the length is there. Now we can use this to just define the length in that X position. In fact, let's do that now. So I'm going to take this vector output. I'm going to use a separate XYZ and a combine XYZ to just take that X component there, just where we want it. And I will just hide that. Now you can see that we have the correct packing in order along all of our points. These instances don't know which spline they came from, so we also need to sample, using the sample curve, an integer, which is going to be the index, as evaluated on the domain, so an integer evaluated on the spline domain. So this is the spline index. Let's just drop it up into this frame as well there. So now our value output from this sample curve can go into the y-axis. And if we just debug this, easy way to debug is with a texture, white noise texture, plug in our y-axis into there. And we can have a look at these, making sure that we're looking at the instance domain. And there we go. You can see that these are now 4 different sets. That last one's not drawing correctly for some reason, but you can see that they are defining different integers. So that's fantastic. That is exactly what we're looking for at this point. Now, before we move on, what happens if we swap over to our fixed spacing? So this is something that you need to do as you're building tools, is just making sure that you are working to the different pathways that you're supporting. So fixed spacing, if I set the spacing to maybe 0.5, hasn't done anything. So we need to make sure that up here, we are also capturing the same data. So I'm going to use a combine XYZ. We're going to be capturing the same vector. And for each point on our curve, so we're going to be using an index. Each point is one lot of this spacing value, this length value, further along the line. So if we take our math note, utility math, and we just multiply the spacing value by the index and plug this into our X, this is essentially how we can calculate the length that each point is along the curves. It's not perfectly accurate, but it is good enough. How do we join these two together? We can simply add them. So I've got this capture attribute here. You can see that clearly it does not exist on this geometry, and vice versa. So this one, if I was to plug this one through, would not exist on the other. So we can use a utility, vector math, and just add them both together. So now, if I tab out, you can see both fixed spacing and non-fixed spacing have a readout for where they are. The other thing I want to do is also store the spline index. So again, we're simply going to take the index evaluated on the domain of the splines. Plug that into our y-axis, and there we have it. Let's collapse that Z socket, and I'm just going to frame these up. So Control J, F2. This one is for fixed spacing. Just really important. I wish I could drive this home even harder, but so important that you give your artists every opportunity to be able to debug and understand what is going on inside these node tools. And I'm saying node tools loosely there. I mean, inside the node groups that you provide them. Geometry nodes is complicated, and for people who do not understand it, it is an absolute labyrinth. So it's important to give as much benefit as possible to people who are sort of breaking into it. Okay, so we've sorted out this array in the x-axis, and we've also sorted out our spline index. So our group ID is dealt with. So let's go ahead. Got our instance on points node here. For us to use the curve deform grouped and the bounding box grouped nodes, we need realized geometry. So let's take a realize instances node, plug this into our grouped bounding box node. The group ID is our y-axis from this incoming vector. And let's just route this around the bottom. And just let's debug this. Let's make sure that we see actual bounding boxes, different bounding boxes. You see that we have these 4 in order. That's all perfect. The min max goes into our curve deform grouped. And these also need the curves passing in. So let's find where our original curves come in. It's up here. So this is, sorry, not the originals, the processed curves. So I'm just going to come up to a reroute, move that reroute along. So I was just duplicating a reroute there and using the Alt right click and drag lazy connection. Join that in. And the next thing that we want to do is just set the position of our geometry to these vectors. Again, we need to make sure that our group ID is working. And that's looking pretty good. Not perfect, but it's well on its way. So another thing that I want to do here, just to make sure that things don't go crazy, is I'm going to force the radius of these curves, just in case they're not at 1. I'm just also joining that to the output switch just so we've got it fixed in. I'm going to make sure that, yeah, the curves are of radius 1, just because we're dealing with the radius in our curve deformed group. And I can just show you that actually. I can scale these up based on the radius of that curve. Maybe you want this, maybe you don't. I'm just going to make sure that we're essentially ignoring it with a set curve radius to 1. There we go. So just forcing it to be a 1, like a unit there. Okay, so if we just toggle in between, something's going on here that isn't quite right. I want these to look almost the same, just a little bit more stretched out, fitted. I don't want any rotation. Clearly there's something going on with the rotation here. So the rotation is a little bit more confusing than just plugging in the rotation like this. And there's a couple of reasons for this. Well, the first one being that this rotation, certain parts of this rotation, for example, the surface normal being sampled from the nearest surface, at the point of this instance on points, we're dealing with this set position. And as you can see, that these points are nowhere near these curves. So what I really want to do is before the set position is to use a capture attribute node, set to vector, and this is going to capture the data about the rotations while the points are in the correct locations. So any sort of sampling that we're doing based on location, 3D space, that is going to be handled before we set position. This can then be used for our rotation. But wait, there's more. You can see a lot of this is messed up. So this is because our curve deform grouped node is already dealing with tangent and normal data. So the tilt is handled and the tangent is handled internally, which means that if we're using a rotation, which factors in the tangent and the tilt, then we're going to be doubling up those transforms, and we don't want to do that. So rather than doing all of that, we're going to take the surface normal, align Euler to vector, make sure there's nothing plugged in before. Still using the pivot on the x-axis, it's just this time we're actually using the x-axis. And we also want this final rotate Euler, which comes from our randomized rotation. So let's just Control-Shift-D, bring that up. Plug in the rotation from our first one with the surface normal. And then this one goes up to our capture attribute. Now what we have is a much, much more consistent rotation. You're going to notice something though. If we toggle this switch, everything kind of flips 180 degrees. And because it's really important that this works intuitively, we want to make sure that the instanced versions of our meshes are very similar. When we turn on Deform, all we want to have happen is for it to stretch to the length of the splines. So what we can do is let's come into our curve deform groups and we're going to just tweak this a little bit. So I'm going to take my normal output from the sample curve, and before I do anything with it, I'm going to invert it. So scale by -1. So that's inverting the normal direction, nothing else. But now you can see that this feels much better. So we just get a little bit of a movement as things pop on to the curve a little bit cleaner. So let's do a little bit of testing. If I come into one of my curves and I press Ctrl T, I get some tilt. If I press Alt S to shrink or change the scale or the radius of my curve, nothing happens. That's what we want. We don't want it to be affected by radius. If I move the ends of these, you can see that we have one popping. This was the final one though, so let's select a different one to make sure. Okay, so it pops on the other ones, but everything is still packed. And that's the main thing. That's the important thing there. So let's come through here. Is there anything else that we need to do? Well, big one is obviously going to be framing. So let's Control J, F2 on those nodes we just added. This one is deform to curves in this main frame. And this instance on curves, let's just give it its own frame. This one is the instances instead. We have this switch at the end. That is fine to leave as is. Now you can always clean up your noodles if you want to. But one thing that I would like to just check is what happens if we unplug surfaces. What if there's no surfaces plugged in? And then we click snap to surface. Well, that's going to be a problem. We don't want anything to disappear regardless of what we do. So snap to surface needs to not happen if there is no surface. So the last thing, this really is the last thing, we're just going to take our group input and realize instances node. We are working on the left-hand top corner of our node tree. Let's take this realize instances node to a domain size. Because we're dealing with surfaces, we're only interested in when the mesh face count is greater than or equal to 1. So it cannot be 0. It has to be at least one face in the surfaces. And then we're going to combine that with our snap to surface boolean. So it only works if both are true. So let's use a math boolean math node set to and. So only when snap to surface and greater than one face is true. So there we go. Let's Control J this last section, F2. This one is going to be called check for surface. So now when there's no surface, just nothing happens. That's all. When there is a surface, you can see it now pops onto that surface, and we can still deform to those curves in that position. We can come in and we can change the tilt of those curves, and with the surface as well. If I rotate that, you can see it's having the desired effect. Final bit of cleanup here, collection on curves. Let's make sure that our output is not instances. This should just be geometry, because it can be either instances or mesh. Be explicit in what data types you're working with here. When making tools, it's important that we just run through and check everything, because ultimately you're going to be releasing this either into the wild or into your studio, and you may not have hands-on access to the tool after you've released it. So let's just go through and make sure that we have things working. So fixed spacing works, and we can still deform that fixed spacing to the curves. Snap to surface works with fixed spacing, and it all seems to be doing a good job. Changing the seed also works. Changing the rotation also works. Great, all of these look good. Let's try turning off fixed spacing. We have snap to curve working, snap to surface, and we can change our spacing a little bit here as well. Let's go back to 0. So obviously negative and positive values are going to work on here. Let's turn off and on snap to curves. Our randomized rotation is working. Our actual rotation is working. Our scale as well on here. And randomized scale, interesting. When our random scale gets too high, what's actually going on? Let's do a little bit of debugging, because this is the fun of making tools for other people, is making sure that you debug your code. What I'm expecting to have happen here, like what is the hypothesis of why this is not working? That I think is probably the first point that you need to come to when debugging. Guess why it's not working. So in all likelihood, the curves themselves are fine. If we select our geometry nodes object and isolate it, there we go. We can see that the curves are fine. Our fixed spacing version did not have this problem. But when we come to our switch, that is a problem. I'm just using Control-Shift left click here to make sure that stuff is happening. Okay, so points. No points are being generated. As we can see here, the count is 0, which means that our points here, this divide for the count is -51. Attribute statistic is -0.5. So the minimum instance size that is coming through, because of how we've set up our scale with the randomness, we've basically ended up in a situation where we have a negative value being the smallest. If we come past 0, what we probably want to have happen is, because obviously they're going to just start getting bigger but inverted, what we actually want to have happen here is for this to just sit at 0. Because we're doing a divide by here, I don't want to divide my length by 0 because that's infinity. Blender will just say not a number and report 0. So again, that'll be an issue. We just want to set this minimum to have a limit, clamp it, just the same as we did for our fixed spacing, wherever that was. We're going to clamp it with a maximum node set to 1 centimeter. So I'm just going to duplicate this down, Alt-P to bring it out of that frame. And we're going to drop it into this other frame, just like this. So now the minimum size is going to be clamped down to anything greater than 0.01. So there we go. Now it's consistent within our node group. And even if we have inverted ones here, you can see them being red from my face orientation drawing. That is working nicely. Now we no longer have any breaks happening. Snap to surface is still going to work with all of this. Excellent. So there we have it. Thanks so much for staying with me. This has been a long tutorial, but this is kind of how professional workflow is. You build tools and then you use those tools to build more tools. And you gradually work up the ladder higher and higher level, building tools which are perhaps more specific use case, like this one you could use for shingles or bridges, or many other things, jewelry, necklaces. But building these tools does take a bit of time. It takes a bit of time not just for coming up with the tools, but also coming up with the basic node groups that you're going to build on top of. And I think it's really important to build on top of these other node groups. Like, that's why a lot of my tutorials are not just, oh, let's make this cool effect. A lot of them are, let's build a tool, because I think it's really valuable for you to build up this asset manager full of individual, like Lego blocks that you can then join together into much larger, much more usable utilities like this. I hope this has been an interesting video. There's kind of a lot for you to get your teeth into, so do check out the links down below if you want to find the original tutorials for those other node groups, or if you just want to grab the start file to work through this one on your own. That also linked down below. This final file as well, if you just want to use this node directly. Hope you've had fun, hope you've learned something, and I'll catch you in the next one.